Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. I posted the solution of this problem on November 10th, 2018, but Darth Vader called and he said, well, he made a suggestion, an offer I could not refuse. Why in the world would I use anything else but Darth Vader rule to find the expected value? So I do have to admit that I should have been more respectful of Darth Vader. So here's the problem. A device contains two circuits. The second circuit is a backup for the first, so the second is used only when the first has failed. A device fails when and only when the second circuit fails. Let x and y be the times at which the first and second circuits fail, respectively. X and y have joint probability density function, and 6 e to the minus x times e to the minus y for 0 less than x less than y. So y is more than x when the density is positive, less than infinity, and 0 otherwise. What is the expected time at which the device fails? And of course the device fails when y happens, when the time of failure y happens. So we really need to just find the expected value of y, because x is the time until the first circuit fails, and then from that time until the second failure, y works in a sense, and we're counting the time until the second circuit fails, which is y. So expected value of y given this joint probability density function. And here's the picture of the story. We have the xy coordinate system here. We are only interested in the area for density to be positive where y is more than x, and that's above the line indicated in this picture as y equal to x. Now fix a value of y and try to find the probability that y is more than y. Well, that happens above the horizontal line where you have that value of y indicated here. Right here is the value of y, and here's the line where you have that constant value. And since the density is positive only above that line, we're looking for the probability of being in that region above y and above the line y equals x. And then we see that the values of y, but we're going to have to give them a different name, so I'm going to call it s, run from that value of fixed value of y to infinity. And then for a fixed value of s, x runs from 0 to s. So we just basically go with these horizontal lines from the level of y and above. And we're going to take a double integral of the density over that region, and that's going to be the survival function of y. And once we have the survival function of y, we take the integral of it to find the expected value. So here we calculate that survival function of y. That's the probability that y is more than y. And as I noted, we let s run from y to plus infinity and x run from 0 to s. And then the density is 6 e to the minus x times e to the minus 2s. So we take the integral with respect to x of that function. And of course, 6 e to the minus s is a constant with respect to x. So it's only the integral of e to the minus x, which is minus e to the minus x, and we evaluate that from 0 to s, and that becomes 1 minus e to the minus s. And you really don't have to do this calculation of integral, because you know that this is the density of the exponential distribution with mean 1, and the cumulative distribution function, because it's the integral from 0 to s of the density, so it's the CDF, of the exponential distribution with mean 1 is 1 minus e to the minus s. So this is what we have, integral from y to plus infinity of 6 e to the minus 2s times 1 minus e to the minus s ds. And we take this as the difference of two integrals, integral from y to plus infinity of 6 e to the minus 2s ds minus integral from y to plus infinity of 6 e to the minus 3s ds. And the first one, if we pull out the 3, then inside we have 2 e to the minus 2s. That's the density, integral of the density of the exponential distribution with hazard rate 2. And of course, since it's the integral from y to plus infinity, this is just the survival function of that exponential distribution with hazard rate 2, and that survival function is e to the minus 2y. So the integral itself is e to the minus 2y. So we have 3 e to the minus 2y. And the second integral is the integral of, if we pull out the 2 and leave 3 e to the minus 3s, that's the integral of the density of exponential distribution with hazard rate 3. So it's the survival function, because we go from y to plus infinity, survival function of exponential distribution with hazard rate 3, which we know is e to the minus 3y. So we really don't have to calculate any of these integrals. We immediately see what they are. And so the survival function is 3 e to the minus 2y minus 2 e to the minus 3y. And all we need to do is just take the integral of this from 0 to plus infinity, because Darth Vader told us so, and we better listen. And so we have the integral from 0 to plus infinity of 3 e to the minus 2y dy minus the integral from 0 to plus infinity of 2 e to the minus 3y dy. Well, okay, I'll just pull out the 3 in front of the first integral, and you have what? Well, you have the integral of the survival function of exponential distribution with hazard rate 2, which is the expected value of that exponential distribution, and that expected value is 1/2. And the second thing, pull out the 2, and you have the integral of the survival function of exponential distribution with hazard rate 3, and that expected value is 1/3. So this is 3 times 1/2 minus 2 times 1/3, and that's 9 over 6 minus 4 over 6, so 5 over 6, or approximately 0.8333, and that's answer D. Of course, that's the same answer we got the kind of more traditional way before, so nothing new here, but a reality is you should always use the Darth Vader rule anytime you have a chance for it. Please remember this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.